So good morning, everybody. I hope you are doing well. We continue today with the equilibrium conditions. So we continue with what we have analyzed yesterday. So basically yesterday, I introduced the methodology to find a resultant force given some coplanar forces concurrent in a point. We said also that a force vector is fully defined once the magnitude, direction, and point of application are defined. So today we will extend this concept to equilibrium conditions. So we would like to find, given a system of forces, concurrent forces still, the force that allows the equilibrium. So basically, let's assume to have a force F1 and another force F2, which for the sake of simplicity, they have the same inclination angle with respect to the vertical plane, which is generally, we call it as y-axis. Instead, the x-axis is the horizontal axis. So in order to have equilibrium, we can approach the problem with two tools, let's say. The first one is the analytical tool, and the second one is the graphical. Similarly to what we saw yesterday. So basically, what do we have to do is to draw the force polygon. So let's assume that our F1 is this one. So we start from F1. Of course, you have to imagine that these forces are applied to a rigid body, for example, and they are applied to a specific point P on this rigid body. We take the second force. So the first force is inclined by alpha, and the second force as well as an inclination equal to alpha. So alpha is this angle as well. Okay. So what is the force that gives equilibrium? The force that gives equilibrium is the force that closes the polygon, the force polygon. So basically what I need to do is to close the force polygon with another force which starts from the arrow of the second one, of the last one, F2 in this case, to the tail of the first one. So this force here is the force F, which gives the equilibrium. Okay? I would like to let you notice that F is the opposite of the resultant force that we saw yesterday. So we can write that F is what? Minus R. Okay, so you can see the resultant force as the opposite of the force that gives equilibrium to the element itself, subjected to these two. What is the type of these forces? We saw yesterday 3 types of forces. What type of forces are these ones? Exactly, concentrated forces, okay? Yesterday we saw concentrated forces, volume forces, and area or surface forces. This one is these two are concentrated forces. So this is the equilibrium condition, basically. And we got it from a simple graphical construction. If we want to obtain the same result, of course, it will be the same result with an analytical approach. So this is the geometrical approach. So we write down that this is the force polygon. Therefore, the graphical method. Next times I won't write any more graphical method, okay? I will just say force polygon, okay? Just to, it's clear that it's a graphical method. The analytical approach instead can be obtained by applying 2 equilibrium conditions, because the system is a system of concurrent forces. If the system was not of concurrent forces, meaning forces was line of action intersecting in one point, because as you can see, these 2 forces have the same point of application, but the lines of action intersect at one point. So in this case, they are called concurrent forces. If these forces were not concurrent forces, 2 equilibrium conditions would not be sufficient. So we would need to use another equilibrium condition, and we will see it in a while. So in this case, we can apply 2 equilibrium conditions. Which are the equilibrium conditions in vertical and in horizontal direction. So we can say that a system of forces is in equilibrium if the vertical equilibrium, considering translation or no, let's say just the vertical equilibrium and the horizontal equilibrium are satisfied. So basically we need to write down two equations. One in horizontal direction and the other one in vertical direction. Okay? Okay, so taking the same exercise, I just write it again. So here we have alpha, and here we have alpha as well. The forces are F1 and F2. Now we are using letters. We are not using numbers because it's more general, but of course in a practical exercise, you will have like numbers, for example, F1, 20 kilonewtons, alpha 15 degrees, for example, and so on. So let's write first the, and we know that the force that gives equilibrium is F. So let's write first the equilibrium in a horizontal direction. The equilibrium in horizontal direction, I need to find the components of F1 and F2 along the horizontal direction, the horizontal axis, which is X. Here, X and Y are implicitly considered, but they are always there. Okay, we don't need to put them in an explicit way, but they are always there. You have always to imagine like a coordinate system. So in horizontal direction, it's very important to consider the real sign of the forces. So that's why we need axes. So just let me write them. So this will be like the axis in horizontal direction. Let's take this point as origin, okay? And this will be y-axis in vertical direction. So as I said, it's very important to find the real sign. So if a force is directed, for example, along the x-axis in a positive direction, it will be plus. If a force is directed along the minus x direction, it will be minus. And we don't have, yeah, just we don't have to be wrong with that, because otherwise the exercise fails completely, you know? So we have to be very precise with signs. Yes, please. The coordinate axis is basically irrelevant, because when you have rigid, as I said yesterday, when you have rigid bodies, you can move force vectors. They are sliding vectors. So independently from the coordinate axis, one force will be directed toward the positive axis or the negative. It doesn't matter where your origin is. Yes. Yeah, right. Also later when we'll see also the moment of forces that probably many of you already know. Also in that case, the pole I mean, independently from the selection of the pole itself, it's the same. The result doesn't change. Okay. So now we write the equilibrium in horizontal direction. So the first component, F1, will be the component projected to the x-axis. So F1x will be this small force. And we need to write it. So F1x will be, now I don't write anymore the arrows at the top, but they are implicit, okay? Because always you have to consider, let's say that F1x is now considered as a magnitude of the vector component, okay? So this is like a definition. So the equilibrium in horizontal direction will be Fyx, which is F1 times what? We have to use alpha, sinus and cosine, sine and cosine. So it will be cosine of 90 degrees minus alpha, so sine of alpha, okay? So if you don't remember these aspects, please study them by yourself. They are coming from high school concepts. And it's positive because the projection, as you can see, is directed toward the positive x-axis. F2 as well. F2 times what? Yes, sine alpha or sinus. Just to be explicit, this is the F1x component, and this one is the F2x component, okay? And then in the force polygon, because this is closed, so we know that this system is in equilibrium, okay? So what other force do we have in a horizontal direction? Minus F, exactly. Do you all agree? So we have only three forces in this system, F1, F2, and F. So the third force is directly the component in x-axis is coincident with the force itself. So it is minus F. So this is an equilibrium condition, so it is equal to 0. And this is the equilibrium in horizontal direction. The equilibrium in vertical direction will be found with the vertical equilibrium. So we'll have F1 times cosine alpha. And now we have F2 cosine alpha. What is the sign of F2? Minus. So we have minus F2 cos alpha equal to 0. Okay. So these are the two equilibrium conditions. Okay. So forgot to write down that the magnitude of F1 is equal to the magnitude of F2 because it's a symmetric problem. Okay. And this comes also from this expression. So from this expression, we can divide everything by cos alpha. And also the second, the right-hand term. This is 0. And this, we can simplify the terms like this. So finally, we have that F1 is equal to F2. So the two magnitudes are the same. Generally, from two equations, we start to solve good morning, the simpler one, okay? So generally, we start from there, and then we substitute the unknowns. So now we take the first equation in here, and we have that F1 is equal to F2. So we have F1 plus F2, everything divided. So we took F on the other side, on the left-hand side. And we have that this expression gives us F, basically. So F, if you want, can be expressed as F1 or F2, 2 times F1 sinus of alpha. So basically, since F1 is given, since alpha is given, you can find the magnitude of F. Okay? So you can find the unknown because the unknown is this one. So you can find the magnitude of this element. Is that clear for everybody? Okay, good. So now I assign to you an exercise that you have to solve here in class with the groups of, you can be 2 or 3 to solve it maximum. And also at home, you must be, unfortunately, you are alone to solve it. This exercise that will have to be put in the portfolio is the following one. So we have a wall in which we have an eye. To this eye, we have 2 forces applied through 2 elements, which are 2 cables. Just a small short definition. What are cables in structures? Cables are elements, structural elements, which are subjected to tensile forces, T or F or whatever. So cables generally are represented with the hinges at the extremities, and they are only subjected to tensile forces. Okay? Okay, so we have 2 cables. One has an inclination with the vertical axis by beta. And the other force as an inclination by alpha. Okay. These two cables are subjected to two forces. Okay. So the forces are F1 and F2. And we want to find the support reaction. So the wall, when you have this eye attached to a wall, then you have two forces, maybe two cables, one maybe to sustain the roof and the other one to sustain, I don't know, a lighting device, for example. So we have two forces applied. And the wall, of course, exerts a reaction force, which must be defined. So this reaction force, in principle, will have this generic inclination. We call it H. Okay? And its inclination with respect to the horizontal axis will be gamma. Okay? So let's assume that it is given F1 F2, so the magnitudes are known, alpha and beta, everything is known. And the unknowns are H and gamma. As any other mechanical problem, like this one, the first thing to do, the first step, is what we told it yesterday, to find the free body diagram. So to isolate the mechanical system and just to focus our attention to the forces involved in the system, including the reaction force, which in this case is only one, because the two forces are applied to a single point. So the free body diagram will be basically, we have the single point, let's say, the force is like exerted in the eye. The steel eye generally it's steel. So we have that free body diagram is F2, F1, of course, with the same directions. In this case, it's not a symmetric problem. In the previous example, it was symmetric. In this case, not. No. And H. So this is the free body diagram. So basically, in this case, we need to focus on the force polygon. So now we don't use AutoCAD, we will use it later. So if you have it, it's better. Now we solve the problem. You should solve the problem. I give you some time to solve it through an analytical approach. Okay. Do you have some questions? If you have questions on the exercise, also from home, okay, also online, I see you and thank you for switching on the camera, which is always nice to see you. If you have some questions on the exercise, just ask it now, so for the benefit of everybody. Otherwise, you can create groups, small groups, 2-3 people maximum, and you solve the exercise together based on what we have just said, okay? Okay, you have, let's say 15 minutes from now. To have the free body diagram means that we have done a cut on the wall, just to be precise on what we mean for free body diagram. We made a cut in the wall and we recreated the wall presence, the wall roll, through the reaction force H. Okay, now we can write down the equations. So we start with the vertical equilibrium, the equilibrium in vertical direction, which is minus F1 cosine alpha, minus because it's directed in the downward direction, okay, minus, plus F2 times what? We need to take the component in vertical direction. So basically, we need to take this component. This component. If this angle is beta, then what is the component? F2 times cos beta. Okay. Okay. And this must minus, let's for the first times I put the equal to 0 just after all the forces, okay, just not to get confused. So we consider all the terms on the left-hand side. So the other component is H. So this angle is gamma, right? So we need to take the vertical component, which is exactly, so minus sinus gamma, okay? And that is must be equal to 0. It must be equal to 0 because we have only 3 forces in vertical direction. Now, the equilibrium in horizontal direction is, first element is F1. So F1 with an inclination of alpha here. So it will be, first of all, we are considering the positive direction, this one, so from left to right. So F1 will be directed in, sorry, because my tablet is not as, so this is the positive direction. So we must consider plus F1. In this case, what? Sinus, sin alpha. Now F2, the horizontal component of F2 is positive or negative? Positive, very good. F2, and sin or cos? Okay. And now we have the H component, which is minus, perfect, because it's directed from right to left. So we have minus H times cos, very good. Cos gamma equal to 0. So these two equilibrium conditions are sufficient because the unknowns are 2. So 2 equilibrium conditions for 2 unknowns. If we had like just 1 equilibrium condition and 2 unknowns, it wouldn't be sufficient, of course. So please remember that when you have 2 unknowns, you have to have 2 equations to solve the problem. The same number of equations. Okay, now we have to handle this system of equations. For example, we can write H sin gamma equal to, I'm just moving H sin gamma on the other side, equal to minus F1 cos alpha. I'm just copying the first left-hand side, plus F2 cos beta. And for the second equation, we have H cos gamma equal to plus F1 sin alpha plus F2 sin beta. Okay? Now, I put like in this way just to simplify the two equations, because what can I do is to divide the first equation by the second one in order to remove H. Because if I divide the left term of the first equation and with by the left term of the second equation, then H disappears, right? But I must be very careful because I have to divide both terms. You can do it. It's possible in a system of equations. So now what I get is tangent gamma, because sin over cos is tangent, equal to minus, please don't put the minus outside the ratio because otherwise you make a mistake. So minus F1 cos alpha plus F2 cos beta divided by plus F1 sin alpha plus F2 sin beta. Correct? Okay, so how can I find that now gamma? It's simple, because now gamma can be found by writing down the arctangent of this expression, the entire expression, minus F1 cos alpha plus F2 cos beta plus F1 sin alpha plus F2 sin beta. And I will get it in radians. So don't be confused with radians and degrees, okay? Especially when you are using Excel or the calculators, because sometimes they generally use radians, not degrees. Now, once that gamma, which is one of the two unknowns, is known, how we can find the other unknown, which is the magnitude of H? By substituting gamma, for example, into the first or the second equation. There is no need to, I mean, you can use either the first one or the second one. For example, let's use the first one. So with the first one, you will have that your H is equal to minus F1 cos alpha plus F2 cos beta divided by, you see, sin gamma. And this is the solution because now we obtained the one and two unknowns. So the first one is the angle, the inclination angle. So it gives to me the direction, the line of action of the force vector. And the second one gives the force magnitude. Okay, so the angle gives, I write it, the line of action or direction if you want. It's not the same. Let's say that the line of action is the line itself. The direction also gives the verse. And the verse can be seen from the, if the free body diagram, for example, is this one. Let me see it. So if the force body diagram is this one, this is F1, this is F2, and the H is this one. Okay. Then what does it mean? That, for example, if H is positive, it means that I have correctly interpreted the direction. If H was negative, for example, we will see also examples about that, especially with reaction forces, it means that the real direction was the opposite one. So the correct direction was minus H, actually. So you can understand also from the sign of H, if in the free body diagram, your assumption of the force direction is correct or not. Okay. Okay, now, during the break, I prepared an Excel file just to show you the some numerical application. So generally, for example, in the midterm, November 5th, I could also assign to you an exercise similar to this one, giving to you some numbers, okay, instead of letters. So you'll have to provide the result in terms of H and gamma. Of course, in that case, as I said yesterday, you can use only a calculator, not smartphone. I tell you in advance, so you have to buy a calculator. If you don't have it, it's just maybe 5 euros, 10 euros. No notes are allowed. So you have just to be able to solve this exercise. So you have all the time in front of you. I mean, you have 1.5 months to prepare yourself to do that. So the example that I prepared is F1, the magnitude. As I said, the magnitude means that we take the vector and we take the magnitude, which is indicated with these two vertical bars. I took, let me see, 8 kilonewtons. So a force of 80 kilonewtons, which is 0.8 tons. As we saw yesterday, equivalences are really important. With an angle, an inclination angle of 15 degrees. Then I took F2, which again is the magnitude of this vector, which is 25 kilonewtons, so much higher, more than 3 times higher, with beta equal to 20 degrees. So these are the numbers that can be different, of course, because once we have solved the problem in letters, every number can be used. So let's then, I share my screen now, or I share the Excel file. Do you see the Excel file from home? Okay, good. Yes, just a moment. Yeah. So these are the assumptions. And this, you can do it also by yourself, okay, with an Excel file, which is nice because then you can see changing the numbers directly the result. It's always important, so we have F1 8 kilonewton, F2 25 kilonewtons, alpha 15 degrees and 20 degrees. Generally, close to these values, I find radians. This is in Italian, so radianti. I think in the English version requires rad or something like that. So because sin and cos want the radians. So I just written the numerator and the denominator. So this is minus F1 cos alpha plus F2 cos beta. And on this part, we have, just let me write it so you can use it. Plus F1 sin alpha plus F2 sin beta. Okay? So this is the denominator. And so here, in this position, you just copy before, which is F2 cos beta. This is inverted, minus F1 cos alpha. This is the numerator, and this is the denominator. So F1 sin alpha, plus F2 sin beta. Okay? So then you have the arctangent of the division of the first one divided by the second one, and you get gamma in radians, which is 0.98 in degrees, is 56. Okay? And H is in kilonewton. H is then the numerator, for example, divided by the sin gamma. So the first equation that we considered. So you see, in just a couple of minutes, or maybe 5, you can find all the numbers you want. Now, I want to show you in AutoCAD. So if you have your laptop, please bring it, open AutoCAD, and we solve the same exercise with the graphical method. Okay? Taking these numbers, so we want to check if this solution is coincident with the graphical solution. Okay. So you can see my screen. Okay, thank you. Okay. And now we can start to draw the, yes, please. I don't hear you. AutoCAD, ArchiCAD is fine, yes. Yeah, perfect. It's the same. If you can rotate lines, it's fine. And I guess you can do that. Okay. So we remove the grid. So we use as units kilonewton, for example. So we just, I draw the line just writing down line. And the first one must be in vertical direction. So we are drawing F1, okay? By 8 kilonewtons. So are you all ready with AutoCAD? I can wait 1 minute if you want. It's difficult. I can zoom in like this. I need to remove this, but I don't know how to do. Okay. Maybe I can like this better. Yeah. Marzi is asking, can you show us the sample of portfolio that you talked about after? Yes, I will show it. It's this one, okay? Do you mean this one, Marzi? If you want to, you can ask. The example is this one, the numbers. Okay, let's come back here. No problem. Okay, so the first thing is let me check if I can maybe this is better, okay? It's the biggest one. So the first line is 8 kilonewtons. So 8, I just make a line of 8 units. And this time I also draw the arrow. Next time I won't do that, just to show it to you. So F1 is down here. So we make the arrow like this. And we have to rotate it by alpha, which is assigned equal to 15 degrees, okay? So we select everything. We rotate it by 15, the opposite, yeah, in this direction, 15 degrees, okay? You just click rotate, then 15, and then it rotates by 15 degrees. Now, the second concurrent force is F2, which is equal to 25 kilonewtons. So you have, first it's better to draw it in a vertical direction, and then you rotate it. So 25 degrees. And I don't have my mouse, so it's difficult to me to use AutoCAD without the mouse. So we make the arrow as well. Okay, like this. So you see the second force is much, much bigger than the first one. And this we must rotate it by 20 degrees from this point. So 20. Oh, it was minus 20. So we just come back, return, rotate in this direction, minus 20. Okay. Okay, so now we built a fourth polygon, for example, starting from F1. So what we do is the copy selection. We move the first force. And we built a fourth polygon how? With the head to tail method. Okay, so we copy selection with this command. And therefore we need to, you see, the tail of the second force is coincident with the arrow of the first force, because this is the head. That's it. So now to close the polygon, let me use maybe, let me see if I can use a line weight. Maybe I can go here. Make it bigger. Okay. So the last vector is it will be this one for sure. So we can mirror it. Let's make it in another color. For example, you can use, if you are doing AutoCAD, you can use also this screenshot of this file AutoCAD to be put on your portfolio. Okay. Once you scan, maybe you leave the space for this and you put it. So this is H. Was a bit, yeah, H. Okay. So now we want to check two things. The first one is the inclination with the horizontal. So it's a line of direction. And the second one is its length. So we go on also on weak properties, for example, and you see here that the line, the length is 19.00. You see here, the length is 19 kilonewtons. Do you remember in the Excel file, it was exactly 19. let us check it. It's important to check. You see here, let me share my screen. You see here 19 kilonewtons, 19.0089. Perfect. Okay. So we are encouraged that maybe we are in the right way. Now we have to check the inclination gamma, which is this one. Gamma in degrees. 56. Let us check it. So with the annotate bar, we go on the dimensions, angular, .56 degrees. Is it right? Okay. So as you can see, it's very simple, actually. It appears to be difficult, but actually is very simple. Because the nice thing is that you can check the results. So if you are not sure about the results, you can check them by yourself. So maybe sometimes you make a mistake in signs, plus or minus, or in sin or cos. It's possible. Also to me, it happens. It's normal. Okay. Okay, so this is done. And now we can continue with the exercise. I mean, with that, let's say I assign to you an exercise. You should solve it. Okay. And this will be also included into the portfolio. So the exercise is this one. So you have 2 cables. As I said, the cables are elements that can be either compressed or in tensile stress. In this case, they are one in compression and the other one in tension. You will have to say what of them are in tension and one in compression. So you have a wall again, so a rigid support. And you have 2 cables. They are also called ties for element in tension and rods or struts for elements in compression. So we will see them. So tie generally for an element which is in tension, tensile state. So if this is the original element, it is subjected to tensile force, and the strut is generally in compression. For tension, you can also use the terms cable in tension, as we have said. Also, you can use ropes, but generally they are not used. We keep tie. And for compression, you can use also the term cable as well. So cable is in general usable for both cases. So we have two cables. One is this one and the other one is this one. They are both attached to the wall. They have a specific inclination. We have two angles. One is alpha and the other one is beta. And here there is a rigid element. So these circles are hinges. We will see them next week. They are typical supports or restraints that give internal reaction. Torkan, about your question, you need to make the portfolio containing all the exercises written by your hand, so on the paper, and then you have to scan them and send them to me 10 days before the exam, okay? So the worksheet is not needed to me. The Excel file is just to you to check if your solution is fine or not. No problem. So we have, as I said, the rigid element, and then we have a weight, so like a cube or of some material, which has a self-weight W. What kind of force is W? Concentrated. Okay, again, concentrated force. And in particular, it was the example that we considered yesterday for a concentrated force. We have said that it's the simplest example of concentrated force. And it's a gravitational force, a gravitational load. So its direction is always directed downwards. So in vertical direction downwards to the center of the earth. Okay, because it's a gravitational load. So you are asked to determine the forces in the two cables. This is separate from the exercise. So when I give you a hint, because just resuming what are the steps when you have to solve a mechanical problem. The first step is to find a free body diagram. Okay. The second step is to solve the equilibrium conditions, which in this case are only two. Because, why? Because the forces are concurrent forces, then the number of equilibrium conditions is just two. Okay. These are the two main steps. The free body diagram in this case thank you, can be defined considering that this element, this cube or parallelepiped, is rigidly connected to, if we give a name to the nodes A, B, and C, to the node B. So this element is rigidly connected to B. So there is no, since it's a rigid body, that's very important. This is a rigid body. To remember yesterday, we talked about rigid bodies. We said that they do not deform and forces can be translated without any effect on the body itself. So we can translate W into B. So basically, we can take the hinge as the point. So W will be this one. And we will have also the cables. Now we know that the cables are subjected only to either tension or compression forces. So basically, as we know alpha and beta, so the given terms are W, alpha and beta. Since we know alpha and beta, then automatically we know the line of action of the first cable and the second cable. One and two. So we already know that we can have like a force, for example, like this for F1. And the force F2 can be either this one or in opposite direction, like going out from the node or toward the node. Also, F1 can be in one direction or the other. The line of action, the only thing which is sure is the line of action, okay? So how can you solve this problem? First, you assume that, for example, the two forces are one in this direction. They are both in tensile. So it's an assumption. So F1 and F2, both in tensile stress. So when a force goes out from a node like this, it means that the object is subjected to tensile force. When the force goes inside the node, it means that the force is the cable is subjected to compression. Clear? So in principle, you don't know if the strut or the tie or the cable in general is subjected to tension or compression, you have to check it with the equilibrium conditions. So how can you start? Generally, it's given by experience. So for example, I already know what cable will be in tension and what cable will be in compression. But if I don't know it, I just assume it. You have to be coherent with your choice. So if the choice is this one, so F1 is directed so that the cable is in tension, and F2 again, also is directed in this direction, you write down the equilibrium conditions as we did, so considering plus and minus signs, and you see. If the result will be a minus, what does it mean? Yes, it means that your assumption was wrong. So you had to choose the opposite direction. And then you can also understand if your cable is in tensile state or in a compressive state. Stop. Okay. Do you have questions about the exercise or any other thing? Is that clear, the procedure that you'll have to follow? Okay. So we want to solve this exercise because you can use the graphical method to solve it. Of course, if you have some questions, I'm always available to answer them to see where is the error. But basically, it's exactly the same as exercises before, with just this, let's say, small complication of the fact that you have to understand how the free body diagram is obtained. But it's the only difference. So you can really play with vectors, actually, because when you start to understand how they can be treated and the components and so on, you can understand better. Okay, so let's take 15 minutes break. So 11:30, we'll start again. Thank you. Let's talk about couples and moments. We are starting lecture now. So couples and moments. Very, very important topic. I would say fundamental. When you have a body like this one, you can have applied on it two forces which do not have the same, they are not concurrent forces, but they have the same magnitude. Okay? And they are parallel. So if you want to have a sight on their line of action, they are parallel. So these two lines, the two yellow lines, are parallel. Is there any question from home? Sept? No, okay.
Sorry, hey, may I speak?
Yeah, you can ask. Yeah, please.
Professor, do you have my voice?
No, if the question regard what you have written, I've already answered to your message in chat, okay? So check the chat.
No, it's about the recordings of the class as we are distant.
Oh yeah, if you want to make a question on the class, yes, please.
No, it's about the recording of the class. I have the question that how should we get the link?
No, we don't hear you. I'm sorry. Your audio is very low. Are you there? Okay, if you have a question, just write it, okay? Because we don't hear you, okay? So we continue now, and then you can write down your question.
Okay.
So these forces have the same magnitude. We can give a definition about what is a couple. A couple consists of two forces having the same magnitude parallel lines of actions and opposite directions. This is a definition. So a couple cannot be reduced to a single force, differently from concurrent forces. Do you remember concurrent forces can be reduced to a single force, the resultant force? Do you remember? Yesterday. Instead, non-concurrent forces, these are typical example and a typical example of non-concurrent forces. So a couple cannot be reduced to a single force. Moreover, it tends to rotate the body because if you apply one force in this direction, for example, let's see my smartphone, for example, in here. You don't see it, you can send it. If I apply one force with my finger in this direction and another force in the same direction, same magnitude, but with opposite direction, what happens? It rotates, okay? So in this case, it tends to rotate the body, and the rotation sign can be either clockwise or counterclockwise. So Basically, for example, the couple that I included here can be written once I find the distance between the two lines of actions. The distance is the minimum distance. So the minimum distance is the distance of the line perpendicular to both lines of actions. And this is h, for example. So for example, this is not a distance. The blue line is not the distance because the distance is the minimum line of action. So it must be 90 degrees. So here we should have 90 degrees. With this sign, with the dot in the square here, it means that it is 90 degrees, okay? So 90 degrees is defines the distance. So the moment m, in terms of magnitude, is equal to what? F times h. There is a right hand rule, let's say, at least in Italy, we use this method to understand what is the direction of the vector, because m is actually a vector, which is located in the third dimension of the plane in which the two forces are contained. In other words, if you have the rigid body, let's assume this is the rigid body, okay? And I apply the two forces, one, let's use one in this direction and the other one in this direction. They have the same magnitude, lines of actions which are parallel, so it's a couple. These two forces generate a couple. So the vector m is a vector which is perpendicular to the plane in which the two forces are contained. And its verse is directed upward. How many of you do know the right hand method, which does like this? Yeah, okay. So you know it. So it's like you take the two forces, you use the right hand, you make like this, and the thumb, just like this, you make the thumb gives you the direction of the moment in vertical direction. So basically, the moment is important to know that it is perpendicular to the plane in which the two vectors are contained. So what is the moment? The moment is the effect generated by a couple of forces. What is the dimension of a moment? For example, this is a question without which you cannot pass the exam for sure if you don't know it, because it's so important. meter, exactly, is, your friend says that the moment has a measure of, for example, kilonewton meter. In general, we can say that the unit is a force times a length. By definition, because it's written here. So you don't have to discover anything. It's written that a moment is the force times the distance. So these are the units. As I said yesterday, we will use the international unit system. Okay? So the moments have particular properties, let's say. So if we have a body, a rigid body, let's do it generic shape. And we have two moments, for example, M1 and M2. So the same body, we can also consider it's absolutely equivalent that M is equal to M1 plus M2. So you can substitute two moments applied on the same body with the sum of these two moments. So it's irrelevant from the point itself. Oh yeah, of course, please. They are in the same direction. They are both counterclockwise. Ah, yes, you're right. Ah, yeah, of course. Yes, thank you. Of course, it must be like this. No, you are right. No, you do well in interrupting me, and because I can make mistakes like this one. So thank you. So yeah, yes, of course, the sum must keep the same direction. Then also the same body. So let's assume that, for example, then this situation then, F and F with same direction, same magnitude, is absolutely equivalent to this situation in which I have the moment. And the moment is equal to H times F. The magnitude, of course. And this is the distance. H. Okay? Of course, for example, in the same body, you can have other forces, like, for example, this force P and P, which have a distance of maybe, let's say, D. So you'll have another moment, which can be translated, for example, here, which is MP. For example, we can call it MP, P times D.
To have, like, in practice, 2 moments in one place. Is it like a beam or something like?
Yes, you can have a beam, for example, where two moments are applied to couples. Yes, even more. I mean, there is no limit. Yeah. Generally, the moments, the couples are seen applied to points, to specific points. But for beams, the issue is different. Because for beams, you don't have rigid bodies. So you can translate moments only for rigid bodies. For deformable bodies such as beams, you cannot do that. Because then the point of application is really significant. In this case, we are talking about rigid bodies. So as in rigid bodies, we use sliding forces, also sliding moments. In deformable bodies, we cannot. There is a strong difference between rigid and deformable bodies. Okay, is that, yes?
By center of the body, how does it create the moment?
In this case, the moment is 0 because the distance is 0. So what you, because in this case, for example, you have this body, you are saying that your forces are, one is this one in the center, and the other one is this one. So this, yes.
I don't say.
Yes, it's the same. I mean, the forces can be applied in all the points.
Opposite side of the center. If they are same side of the.
Ah, yes. Ah, yeah. They create a moment. Yes, of course. They can. They can. For example, you should come here. Because I don't know how to. If you apply one force here, the center is this.
The both of them in the one side, like outside of the center, both parallel forces.
Yes, like this. You are saying this. This is the center, 1 and 2, for example. They can rotate the body, of course. You can see it like this is the experiment. One force in this direction, the other force in this. Yeah. Yes, they can. Come. Yes. You see? This is the center. I apply a force here, another force here.
But this is much more, or the far from the center, and
Yeah.
the torque is probably.
Yes,
higher,
it will be maybe very, very small, but it will rotate still the element.
But the calculate method is the same or not? Is anything changing?
It depends on H and F.
Okay.
It can be even very small, but there is a rotational effect always.
But it's the same for these one.
Yes. If the body is rigid, yes.
Because in now we okay.
I understand your point, because you imagine that if you apply like here, it rotates more, in your opinion. If you applied it here, it rotates less. But you have to imagine that, I mean, the equivalent moment is always the same. It will be greater if you are far away from the center.
Yeah. Why we don't measure from the center?
You can.
In this.
Yeah, you can use it. Also the measure from the center. Yes. Maybe we can also talk later. Yeah, in any case, it's the same. Okay, so let's go back. Let's continue. Now, this is a very relevant concept. The moment with respect to a pole. A pole is nothing else but a point, okay? A point that we choose. So let's assume we have a force, for example, in this direction, P. And we want to calculate the moment we have a body, okay? We have a body. And point O is the pole. So the point with respect to which we want to calculate the moment, okay? So how can we do? So we simply apply the formula. So the line of action of the force itself is this one. So we need to find the minimum distance from the force itself to the line of action. Okay? So the minimum distance will be this one, the 90 degrees direction. So this is 90 degrees. Okay? So this is h. So the moment is given, the moment given by the force P is equal to P times h, or L, whatever. And h is called the lever arm of the moment. Okay? So this is important. We will use this expression really a lot when we'll have to solve exercises, especially with beams. So now we are ready to, with this definition, we are ready to solve an exercise considering also moments. So let's see this example. We have a rigid beam like this. It's like the swing that we saw yesterday in the example. And we have a support, which is a hinge. As I said, next week we will see the supports, which is a really important topic in structural engineering. So this system is in principle not in equilibrium like this because the beam is rigid. If you put a rigid beam on a hinge, what happens? That due to its self-weight, it falls down, probably from the side with longer length, so the longer part. So we call the two forces, we have two forces, we call them P and Q. And this generic distance is, the total distance is L. And we assume that this shorter distance, so from the left extremity, is A. So this can be like, I don't know, 1 meter, 2 meters, L can be 5 meters or so. So we want to find, we are asked to find A, so that the system is in equilibrium. Also, you're asked to find the support reaction. So we find the support reaction, we call it R. Exerted by the support to the beam. Okay, so you have two requests which are connected, of course. Okay, how to solve these kinds of problems? Basically, up so far, we know that we have two equilibrium conditions, one in horizontal direction and the other one in vertical direction. When we have the rotation of the body, we have to add also the moment equilibrium, the equilibrium in terms of moments. So we have to write down three conditions. The first one is the sum of forces in x direction for I, which goes from 1 to n, equal to 0. So this is the equilibrium in horizontal direction. The second one is the sum from I equal to 1 to n of Fi y in vertical direction. I is the number, is the generic ith force. So if we have n forces, this is a general expression for the equilibrium conditions. And the last one is the sum, again, from I to n of the height moment with respect to a pole P point. Let's use maybe another term because we have already P. Let's use O, equal to 0. So these three are the equilibrium conditions. The third one is the new one that we are going to introduce, is the equilibrium in terms of moments. Okay? So what is the first step we have to do anytime we face with a mechanical problem? The free body diagram. So we need to understand this mechanical model, how can be transformed also from home, and you can answer my questions, so we can interact also in chat, or you can switch on your mic. So we need to substitute this beam with its forces, considering the support reaction. Now, probably you still don't know it, but I tell you, this support is a support which gives, actually it gives two reactions. One is this one and the other one is this one. But we just consider the vertical reaction, which is R. So R is the force exerted by the support to the beam. So the free body diagram is this. We remove the support. And in the free body diagram, now we can put the forces. So P and Q remain the same. And here we have the reaction force, which at the moment is unknown. Right? So how can we solve this problem? So we write down the equilibrium conditions. So in horizontal direction, what is the equilibrium condition? 0. So the first times you can write the equilibrium condition, but you know that is 0, so you can also omit it, but it's there, still it's there. The vertical equilibrium is very simple. Can you tell me? Is minus P, we keep the same convention, minus P, minus Q, perfect, plus R, equal to. Is that a weight? No, negligible weight. Okay, we write it. Negligible beam weight. We have only these two forces to simplify. Now we have to write the equilibrium in terms of moments. We can choose a pole, for example. We can choose either this one, or this one, or this one, or also another point in the middle of the beam. But you have to be clever, you have to be smart. You should choose a point that vanishes at least one force, possibly many forces. So the smart solution is to choose either point through the line of action of P, or through the R's line action, or Q's. One of the three. Okay? I don't know. For example, we go with the first one. We choose A as the first example. And we assume that the counterclockwise direction is positive for the moment. So we will have the first couple, the first moment is R times what is the minimum distance from the line of action of R to the pole A. A. R times A. Positive because it's counterclockwise. Then what is the other contribution? Minus Q, yes, exactly, times L. Perfect, because L is the total length of your this is L. And this must be equal to 0 because we don't have other forces. So from the third equation, for example, the third equation, we know that we write it, first of all, R times A equal to Q times L. And from it, we know that A is equal to, it's better to combine together forces and keep separate geometrical terms. So Q divided by R times L. You have always to check if the dimensional analysis, is called dimensional analysis, is satisfied. It means that the units are correct. For example, A is a length equal to Q is a force. So force divided by Q is a force as well. And L is a length. So it's satisfied because F and F goes away and the two lengths remain. So you have always to be sure that it is correct. Now, what do? You go to the second equation. Now you have the value of A. So you can, actually the second equation gives you P plus Q. You put them on the second hand side and then you change and you have, this is the second equation. Okay. So you need to find R from the previous equation, which is Q times L divided by A. Now you substitute R in this equation. Because now the aim is, the purpose is to have just one unknown in one equation in order to solve it. It's clear. And therefore you have P plus Q equal to Q times L divided by A. So from this one, it's simple now to find A, because A is equal to Q divided by Q plus P times L. Okay? So once you have A, you can also calculate the magnitude of the R vector. So you take this expression in here, you put it here, and you can compute now A, because this will be like Q divided by Q plus P times L, and you can handle it in order to have an ordinate expression. So for the next time, you can assume that you have P, the magnitude of P, which is P without any arrow. Let's assume it's the play that we saw yesterday in the syllabus, so you can check it. It's maybe there is a child, so let's say 20 decanewtons or 25 decanewtons, which are kilograms, force kilograms. Then we have Q. Maybe the father is, I don't know, 80 decanewtons. And also you must know L, which is 3 meters. So find A and R. You have already the formulas. And something that you can do to check if your result is correct is to change the pole. So if the pole before was the left extremity, so if the pole before was A, you can check if your result is correct or not by, for example, choosing the pole as B or as C. So by changing the pole, you can check your result. Of course, the result must be absolutely the same. Otherwise, you have made a mistake somehow. Okay? Okay. Do you have questions about that? Do you have classes this afternoon? How many hours? 4. Some faces are like desperate. Yeah, it's difficult, I know. Okay, then let's do like this. Now we take a very short break so we can finish a bit earlier, okay? Maybe we take a short break of 5 minutes. Then we introduced just a couple of, another small topic, and then we finish, let's try to finish as soon as possible, okay? Coming back to the exercise assigned for the next time. What I would like to point out is that these two elements, A, B, and BC, are like rigid sticks. Okay, so your friend told me that generally you intend cables as like elements only working in tension, which is true also in my experience. Cable is generally, but I'm trying to keep in the same definitions reported in the book. So in the book, there is this expression. But if you get confused with that, we can simply remove this. So when we talk about compression, we talk about a strut. Okay? So cable just for tension, if you prefer. It's just a convention. Because sometimes cables like ropes are flexible, and therefore they are like not rigid, being flexible. So these two elements are like rigid sticks. So we can define the forces in the two structural elements, for example, just to be. And this is why then you don't know in advance what is the element with the tensile force and with the compression force. You don't know it in advance. You have to find it out, as I explained before. Okay? Clear now for everybody? So we will use cables for tensile forces and struts for compression. Or I will say compressed elements and so on. Now, let's introduce topic which you should already know. So as I told you, the first 1.5 weeks will be dedicated to a recap of basic mechanics. So what you should know, then we'll go more in depth in the structural engineering aspects. So centroid of forces. So let us assume we have a plane, like a plate with a certain thickness. And we have also, as usual, a coordinate system, because when we have to solve analytically some problems, we need also to know what are the axes. So we assume that the origin is here, the z-axis is this one, the x-axis is in the middle plane x, this one, and the y-axis is this one. Okay? So let's assume that we have different forces acting on this plate in vertical direction. So they are all vertical forces. They are called G1, G2, G3, and so on, Gn, Gi up to Gn. So we have a number of 5, 6 forces or so. So we can find a point which is called the centroid of forces, in which we can apply the resultant force G, the force resultant of all the forces, which has the coordinates. Here is, let's change the axis. Okay, let's do it. Here is X, and this one is Y, sorry. So the distance from C, so G is a force. The distance from C to the y-axis is called XC. Okay? And the distance from C to the x-axis is called YC. It's the coordinate system. I mean, nothing so different from what we just know. All these are forces. So let me write also the arrow in here, just to be sure that you know that these are forces. So now, what do? We want to find C. So the centroid of forces is basically the point, the centroid is the point in which the resultant force can be applied without changing the effect of the single forces. So I repeat, the point C is the centroid of forces, Gi, for I, which goes from 1 to n, applied in which the resultant force G, so G is the resultant force, is applied. Doesn't make any sense. G is the resultant force. C is the centroid. of forces GI for I, which goes from 1 to n, if we have n forces in the system. Okay? So the position XC, so the abscissa is called, of the centroid, is given by the sum of the products GI times XI. XI, what is XI? XI is the distance from each force, the application point. So for example, in this drawing, XI will be the distance from GI to the x-axis. Okay. Here, I don't know why I put the distance in a wrong way. The correct distance is to the axis, of course, not to the black line, is to the purple line. So this xi is the distance of the generic force. So you have to make the product of all these forces, and you must divide this sum by the sum of all the forces. It's a kind of average mean, weighted with the weights, which are the distances of the single weights from the axis. It's possible to demonstrate this formula, but we won't do that, okay? Because we don't have enough time. So YC similarly is the sum of GI times YI divided by sum of GI. Okay. It's important to say that the resultant of forces must not lead to a couple. Otherwise, this formula is not valid. In this case, we don't have any couple, any moment. Otherwise, this formula is not valid. Okay? Now we apply this concept to an example, a real example. So as you can see, these are length because XC and YC are length. And now let's look at an example. So we have a beam. These are the supports. Now, don't worry if you don't know what are the supports. They are just two supports of a beam. And this beam is loaded by a constant distributed line load. So the line load is, we generally call it as Q. The unit of Q is a force over L, or Newton to meters, for example, or kilonewton to meters, kilonewton to millimeters, and so on. Many times your friends and colleagues at the exams, they exchange Q for Q capital letter or P. So they think that Q as distributed load or line load is the same as Q, a capital Q. Absolutely not. It's a severe mistake because it's a lot, really remarkably different line load, which is Q. Q is called a line load or distributed load, which is different from Q, which is a concentrated load. The line, in particular, the line load, what is the line load? We saw it yesterday. Kind of area or surface load when one dimension of the area is vanished. So these are absolutely different actions. They cannot be confused one with each other. Okay, so we assume that O is the origin of the z-axis. We consider the z-axis in here. And we want to find, or we let me write x. Z is the same, but I want just to keep the same letter as before, just not to confuse your minds. So x is the same. We would like to find the centroid C, the centroid of forces C, and the resultant of forces. So we want to find Q, which will be, for example, this one. Yes, the resultant is a concentrated force, but the line load is not a concentrated force. So the resultant of a line load is a concentrated force. As I told you yesterday, the concentrated force is only an idealization in nature. It doesn't exist. Okay, so XC. Now, since we have a distributed load, what can we do? We have to use integrals. Don't worry, it will be only a few times we'll use integrals. This is one of the cases. So first, it's better to find Q, the magnitude of the force. Instead of using sum, so discrete sum of elements separated, we use integrals. So we use integrals generally when we have functions, when we have continuum elements. Okay? So the magnitude of Q is equal to the integral from 0 to, let's assume the beam span is L. Okay. So this is L. From 0 to L of Q. In principle, Q is variable with X. We assume, for example, is variable. This is Q in general. We don't know at the moment. Qx is variable. Qx in the X. It's the integral. But now we know that our Qx is constant. So we can write Q because it's the same for all the points, right? So we can put Q out of the integral. So it will be Q integral from 0 to L dx. Integral from 0 to L dx is equal to this integral is equal to L. Who said that? Yes, L. So Q times L. So the resultant force, even if you don't know what are the integrals, okay? I mean, you should know actually. Q times the length over which this load is applied gives the resultant. And indeed, QL is a force because it's a force over length times length. Clear? Now, this exercise, I give it to you. We will solve it together next week. Same beam. Same. But with a triangular load. Like this. Okay, where the maximum load is Q. So Q is the maximum in the right extremity. Okay, so still we have, so you are asked to find the resultant Q and the centroid position. Hint, the origin of the axis is still on the left extremity. For example, X is always the horizontal axis. What you have to do is you have to recall that. So you have to understand that the function ruling Q, so Q now is a function, is equal to what? Is equal to X divided by L, where L is the beam length, times Q. So it's a linear function. Indeed, if you have Q equal to 0, is equal to 0. And indeed, this point is equal to 0. For X equal to 0, we are on the origin, and Q is equal to 0. You see that Q is equal to 0 here, yeah? In the other support, so in this is O, this is A. In A, in the node A, you have the maximum line load, which is, so for Qx equal to L, we have what? L divided by LQ, so Q. So you must use in the integral, because you have to solve it with the integral, this expression. Actually, there is a topic left, but we finish for today because I see you a bit tired. So we will retake this aspect next week. Do you have some questions before leaving? Okay, thank you then for your, yeah, please. From previous years, what? Midterm for what? No, it's the first year we introduced it. Last years we had group projects. So this is the first year. But it's like the exercise. As you write the exercise, you're writing in your notes. It's good. I mean, like they are written here. Yes, it's better you take it, you bring it, yes. Bye-bye.